So I'm recording. This is specifically a structural analysis engineering question. So it's only applicable to people who are kind of doing structural engineering, civil engineering, stuff like that. I guess it can be used in different departments of engineering also. But specifically, at least for me, it's civil and structural engineering. I'm going to use a specific method. There are lots of methods to use, but this is the one I'm going to use. So we basically take apart all the joints. So we have element AB, which is just this one, if I can get it to be... okay, I guess I can't draw there. But basically, it's just the element from A to B. And we can find that the stiffness is 4EIL over the angle, which is, I believe that I'm having an issue with this, so I should be now able to draw on it. Here we go. So it's this one, 4EI over L. Okay, so that's the stiffness for AB, so KAB or BA, whichever way you prefer to do it, is 4EI over L. But here we see that it's actually 2I, so it actually equals 4E times 2I. And then the length we see is 8. So it's over 8. So that gives us simply EI. Now we do the same for BC. So KBC equals, and then let's look at the element. I see a pin. So what one do we use? Well, we use this one. So 3EI over L. However, we see that the length is 4. And we have second moment of area 2I. So it actually equals 3E times 2I over 4, which equals 3 over 2EI. Okay, now we do BD. And we basically do the same as we've done the other stiffness, and we use 4 equals EI over L. L is 3, and I is just 1I, it's not 2I this time, so it gives us 4 over 3 EI. Now we need to do the distribution factor, which is the factor of stiffness between each element. So let's look. dB A equals... And now basically we're finding the ratio between each element. And so the ratio of stiffness for BA compared to, so at joint B, so it's all element AB, BC, and BD equals EI over the sum of all the stiffness, which is 23 over 6 EI. So the distribution factor is 6 over 23. Let's do the same for DBC. So it's the same way to work it out. We're just doing the ratio compared to all the stiffness that we've already calculated. I'm sorry, it's 23 over 6 EI, which gives us 4 over 23. And then we can find, because obviously the ratio has to add up to 1, or all the distribution factors add up to 1, so you can just find out the final one by dBd is 1 minus 6 over 23 negative... Wait, no, sorry, I've done that wrong. Let's just do it originally how it's done, just to make sure that it is correct. Okay, so there we go. We have all the distribution factors. Wonderful. By the way, this is found out, and I'll just show you here just to make it easier. It's the sum of all the k's. which is EI plus 3 over 2 EI plus 4 over 3 EI, which, when we add it all up, is 23 over 6 EI. Perfect. Okay, now what do we do? So we've done the first two steps. So the stiffness is the first, distribution factor is the second. Now we do the third, or at least my third step. And we find the fixed end moments. Okay, so let's first start off with AB. That's what we've been starting off with, so let's do that for the moments as well. So the moments of BA equals... Now, we've got a UDL over the top of this frame, and we know how to do that. It should be memorized, but it's also given here. So it's just, and we do it negative, in this case, 12. So if we put all of them up together, it's 20 times 8, because we've got the length and we've got the uniform UDL. And that gives us negative 106.7 kilonewton meters. And therefore, BA, so on the other end of this element, it's just this, but positive. So MBA equals 106.7 kilonewton meters. Because we've got to remember that these are all balanced. This is a frame that is standing up. So they should all be balanced. And this is kind of what we're doing. We're getting to the point where we can balance all of them. So at each joint, the sum of all the moments is 0. So let's do MBC. And we don't have to do the element BD because there is no UDL on it. So we just assume it to be 0. So it's the same process, just L over squared. I'll quickly walk through it. However, this is something that's really easy to miss out. We're accounting for the effective length, right, of this, and because we know it's pinned, you actually times it by 1.5. Very easy to miss out. In fact, there have been times where I've missed it out, which is not good when you're in an exam. But you still do get carryover marks if your professor is nice. But we just find this to be 40 or negative 40 kilonewton meters. Perfect. And obviously it's just the positive at the other end of this element. Okay, now we get to the good bit. This is, I'm probably going to make this smaller just so I can fit the rest in. So I'm going to make it smaller. Should all be able to see that still. Okay, now we have to do, or at least there's different ways of laying this out. I personally differ depending on what the frame looks like, because sometimes you've just got a beam and it's just got different supports and stuff like that. But because we've got a frame here, it's easier to do it like this. So once you do a few of these questions, it should become clearer and clearer on why you can set it up like this. So we've got AB, and we've got, sorry, I'm actually just going to really messily write this down because this video is going on for a while, and it can be boring just watching people write things down. So B, C, and then let's just do it here. We've got, oh sorry, that's actually BA, and then BC here should be, and we've got BD. Perfect. Oh, that's gone weird. And then we've got another, and then we should just have our final thing here. We've already figured out the distribution factor, and we just assume like the 1 and 0, it's just because there can be no moments at specific points, specifically when, you know, different parts of the structure, depending on the support, it can only equal 0. And so we have that here, and then these are just the ones that we've already figured out. 9 over 23, 8 over 23, and then we also have 0, 1 here. Okay. So we have the free end moments, and we have already figured out a lot of these, haven't we? So we'll just write them in. Let me just write these in a bit clearer, because I'm not doing a very good job at this. Negative 40. Yeah, and that's literally all we've got. So it's actually not looking too bad. But we do see that the sum at the joint B is not even. Okay. And so what we do is we times the difference in the joints, and we times it by the distribution factors. And so what we do here is it's negative, because I've done this previously, so I've just times them myself. You can just times them yourself to kind of understand. And so this is the difference, difference in free end moment at joint B. Cool. And then it's times by distribution factors. And then we also have to times by a half. This is just something you do to the other part of the element. So negative 8.7 half 11.7. Okay. Is this already balanced? Let's see. So we sum it all up. And what do we find here? So we find here that we can just 11.5. And then let me actually just make another line, just make it clearer. Sum 115.4. And this is actually looking quite good. 66. We'll have to add up all of these together. 7 and 11.7. So sum equals 0. Or not exactly 0, but close enough. It's between 1% of the value, right? So it's actually kind of 0. But we don't have to go further. It just makes it more complicated, and we're close enough to the answer already for the exam markers to say, yes, they've understood, this is right. And now we got to remember, so technically we found the bending moments of the diagram. However, we haven't drawn it. So part B is here. So let's just draw the frame. Okay. We've got, as we see here, 115.4. Because we know there's a UDL, it looks a bit like that. What's it here? 89.2. 115.4. Just going to draw this in. This isn't to scale. When you sketch this, it should be more accurate. I'm just doing it because I'm not very good at drawing on an iPad. Okay, and then we also know that for this, it gives us 66. So we go 66, and again, it's a UDL, but the other end of the moment is 0 because, as we can see, pinned. Okay. I will find out these points after I've written this initial point down. 0. Okay, and then we actually also have the final one. So it's 23. Yeah. The final one. And we have 11.7 and negative 23. So 11.7 It's actually negative 11.7 and 23.0. I think it's actually 23.3, and I've calculated wrong. But it's so close that I am not going to redo the video. Okay, now we've got to find the midpoint, as it says here. We've got to show the values and midspans of the beam. How do we find the midspan of the beam? Well, we find the difference between the two values. So mid at AB equals half of the two end moments. Okay, and then we actually look at it and we think, oh, actually there's a UDL as well. So we times it by the UDL. We negative it by the UDL. L squared over L. Over 8, sorry, not L. That equals 20 squared times 8 squared over 8. And we find that out to be negative 57.7. Does that look right? Yes, it does. Negative 57.7 at the midpoint. Okay. Mid at BC. We basically do the same thing, just with different values. So we have 66 plus 0. Very simple. And then negative WL squared divided by 8, which is just 20 times 4 squared over 8, equals negative 7.0. Much smaller, but makes sense given the values. Okay, so that is it. Let me just put the joints on. Cool. So that's the question, 20 marks. Normally you're given a few hours to do about 100 marks. So you can actually spend a long time on this question. It's very kind, really. But you do have to know it, and it's very easy to go wrong. As you can tell, this is actually negative 23 point, oh no, not negative, 23.0, 20, oh no, 3, sorry. So this is the final result. This is all the work that's gone into it. It's not too bad once you get around to it. Just really practice makes perfect. Hope this is okay. I know it's messy. Still getting used to how to draw on this thing. Yeah, hope everything's going well. Hope that this is useful to you. Good luck on any exams that you might be doing.